Imagine you have a square piece of material. To turn this flat sheet into an open-top box, you must cut equal squares from each corner and fold up the sides. Our goal is to determine exactly how large those cuts should be to ensure the resulting box holds as much as possible. To proceed, you need to remember the basic volume formula for a rectangular prism. Volume is the product of length, width, and height. By substituting our expressions for these dimensions, we can create a single function where volume depends entirely on the size of the cut Ex. The core of optimization is finding where a function reaches its highest point. In calculus, we know that at a local maximum or minimum, the slope of the tangent line, or the derivative, is equal to 0. This is the stationary point that reveals our optimal value. Let's build our objective function. By multiplying the height x by the square of the base 20 minus 2x, we get our volume function. Expanding this polynomial into for x cubed minus 80x squared plus 400x makes it much easier to differentiate in the next step. Every physical problem has constraints. The cut x cannot be negative, and it cannot be more than 10, because cutting 10 from both sides would leave no cardboard at all. Our search for the maximum volume is restricted to this specific interval, known as the feasible domain. If we were to graph this function, we would see the volume start at 0, rise as the box gains height, but eventually fall back to 0 as the base disappears. The peak of this curve represents the maximum possible volume we can achieve with our 20 by 20 sheet. Now, we apply the power rule of differentiation. The derivative of for x cubed is 12x squared, the derivative of negative 80x squared is negative 160x, and the derivative of 400x is 400. This new equation, v' of x, represents the rate of change of the volume. To find the maximum, we set the derivative to 0. This gives us a quadratic equation. We can simplify the math by dividing all terms by 4, leaving us with 3x squared minus 40x plus 100 equals 0. Now we just need to solve for x. We can solve this using the quadratic formula or factoring. We find two critical points x equals 10, and x equals 10 divided by 3, which is approximately 3.33. Remember our domain? X equals 10 results in 0 volume, so our optimal cut must be 3.33. By plugging our optimal cut of 3.33 back into the original volume formula, we find the maximum capacity. The base dimensions become 13.33 by 13.33, and the height is 3.33, resulting in a total volume of approximately 592.6 cubic centimeters. How do we know for sure this is a maximum and not a minimum? We use the second derivative test. The second derivative is 20 for x minus 160. Evaluating this at our critical point gives a negative value, confirming the graph is concave down and we have indeed found the peak. What if the sheet isn't square? Let's look at a 15 by 10 rectangle. The logic remains the same, but the symmetry is gone. The volume function becomes x times 15 minus 2x times 10 minus 2x. The resulting quadratic for the derivative will be slightly more complex. Expanding this gives us for x cubed minus 50x squared plus 150x. Taking the derivative yields 12x squared minus 100x plus 150. Setting this to 0 and using the quadratic formula will give us the precise cut needed for this specific rectangular sheet. Notice how the optimal x changes based on the aspect ratio of the starting material. In the square sheet, the cut was 1/6 of the side length. For rectangles, the ratio shifts, but the calculus method remains the reliable tool for finding the answer every time. In more advanced scenarios, we might want to minimize the surface area for a fixed volume to save on material costs. This is the dual of our current problem. Instead of maximizing volume with fixed material, we minimize material with fixed volume. Optimization isn't just for boxes. Consider a soda can. Manufacturers use calculus to find the ratio of radius to height that uses the least amount of aluminum while still holding exactly 355 milliliters of liquid. This involves differentiating the surface area formula. In real-world engineering, you might have multiple variables like heat resistance or weight limits. While we are using single variable calculus today, the same principles expand into multivariable calculus using techniques like Lagrange multipliers to handle multiple constraints simultaneously. Always check your edge cases. If your math gives you a value that is physically impossible, like cutting so much that the box has no bottom, you have likely found a local minimum or a point outside the feasible domain. Logic must always accompany the math. A common mistake is forgetting the height variable x when setting up the volume equation. Without x, you are just calculating the area of the base, not the volume. Always ensure your units are consistent. Length times width times height must equal volume. What's your exponents? When using the power rule, the exponent must decrease by exactly 1. A small error in the derivative will lead to an incorrect critical point, making the entire optimization process fail. Double-check your differentiation before solving for 0. Calculus will often give you 2 or more solutions. You must check which one makes physical sense. If one solution for x is larger than the sheet itself, discard it. Only the value within your defined boundaries is the true physical maximum. To summarize, first, define your volume function based on the physical dimensions. Second, find the derivative. Third, set that derivative to 0 to find your critical points. Finally, verify your result using the second derivative test or the context of the problem. Optimization is a powerful tool. By understanding how to model a physical situation with an equation, you can use the power of the derivative to find the most efficient solution possible, saving time, money, and materials in the process. Here is a quick challenge for you. If you have a square sheet with a side of 12 units, what cut x would maximize the volume? Use the shortcut we noticed earlier or run the calculus. If you chose x equals 2, you are correct. Solving the challenge, for a 12 by 12 sheet, the derivative leads to x equals 2 or 6. Since 6 would consume the whole sheet, 2 is our winner. Thank you for exploring calculus optimization with us. This video was generated by VisionSolve AI.